A special lecture on ML Type Inference. This is video number 4. We learn freely generated set and implicitly typed Lambda calculus. First, additional topics on inductive closure. In video lecture 2 and 3, we have learned inductive closure as a mathematical basis for defining languages such as lambda terms and types and analyzing their formal property through induction. There are some related concepts related to this inductive closure, namely freely generated set and recursive function definition. These are apparently useful in formal analysis of programming languages. So this video lecture gives the overview, only overviews. So for more details, please consult a textbook, namely this section, or any other textbook on mathematical logic or formal language theory. And we are not go into the details of this concept because this is not really necessary to understand the rest of this lecture on type inference system. So only overview. First, let me give a definition of freely generated set. This is a restriction on inductive closure. So when an inductive closure named X satisfies the following conditions, 3 of them. First, this intersection is empty for any distinct pair of 2 elements in F. This is the first condition, right? So we know that this is a notation that set of all elements of the application of this function to this set. This is a x to the n. This is the n tuple of this inductive closure, same as g of x, right? So the first condition is that the intersection is empty. And the second condition, for any function in f, this intersection is an empty set, right? And the third condition, for any f in this set, the restriction of x onto this x to the n. So this is a restriction of f to the elements taken from this inductive closure. This restriction is an injective function. Then we say that x is a freely generated set. So this condition is actually a condition on this constructor function f. So these condition f intuitively represent any constructor function f always generates new elements. So this intuitive property, you should think that this is an ordinary, natural property of any language definition or any definition consisting of syntactic object. So in what follows, we implicitly regard an inductive closure as a freely generated set. Under this implicit assumption, we understand the following. A grammar such as BNF specification defines a set of parse trees, not a set of string. Set of string are often ambiguous, where a set of parse tree, each element completely determines the syntactic structure. Similarly, for a proof system defines a set of derivation trees of formulas or sequence, and not a derivable set of formulas or sequence. Sequence are just a logical sentence. This is a terminology denoting some statement in logical system, right? So freely generated set as a restricted class of inductive closure, this provides a basis for mathematical basis for recursive definition of function. This property is represented by this theorem. So let A be any set and X be a freely generated set. Now we assume that for each C, there is a given overline C in set A, and for each f function there is an overlying function on a to the n to a. Given these overlying objects for each c and f, so you can understand these overlying objects as interpretation of corresponding syntactic object. Under these given semantic element, the theorem says there is a unique function phi from x to a satisfying the following conditions. First one, for each constant c in this set C, application of this phi to C is equal to this semantic interpretation overlying C. And for any element constructed syntactic object constructed by this function f in this freely generated set, application of phi to this constructed element is equal to, first you apply phi to each element in a given tuple, and you make a tuple in this space, semantic space, and then apply this function overlying f. Then you get the same element. So this function phi is called the unique homomorphic extension of this function. This is simply a function taking constant c and return its semantic interpretation. So this phi is a unique homomorphic extension of this function with respect to this semantic interpretation of each constructor. So this theorem guarantees that a recursive function definition on a freely generated set indeed determines a function. So according to my policy of this lecture, namely to explain various concepts, in particular complex and abstract concepts in a clear and easy to understand manner, with respect to regarding this policy, the properties I have just gone through are a bit abstract. So let me elaborate the intention of the theorem. So this theorem is about recursive definition of functions. So imagine that you define some property on a syntactic object like expression, say the meaning or interpretation of expression. Then typically you do, for each constant you interpret the constant, right? And then for compound syntactic object obtained by this syntactic constructor, interpretation of this element, you first interpret the argument, and then according to the intention of this syntactic construct, you calculate in the semantic world the result and obtain a semantic element. So this is the usual way of defining some property recursively. So recursive definition consists of two classes of equation. First of this is this shape, and the other one is induction. So you do this way. However, these two classes of equations do not necessarily yield a well-defined unique function. So this theorem guarantees that in the case of freely generated set, you always get a unique, well-defined function by only specifying these two classes of equation. So this is the intention of the theorem. So at this moment, let me review the contents of the lecture. So far, we have completed inductive definition of languages and proof by induction through the notion of inductive closure. This part covers the textbook chapter of these. And now we turn to type inference. In this video, I start with untyped lambda calculus and then go into implicitly typed lambda calculus and then define a formal system called small lambda. So for further details, consult. So these chapters are the chapters of my Japanese textbook, and as I said in the beginning of this lecture, the video number 1, the unfortunate situation is that this textbook is only available in Japanese, and so I have some intention to make an English summary or a lecture note in English and make it available to the audience, but not yet. So in future, this is only my intention in future, and unfortunately there is no such thing. So for further details, consult the textbook or other books on programming language theory. However, as I stressed at the beginning of this lecture, I organized this lecture self-contained so that I detailed each important definitions, and also for major property like theorems, like completeness theorem for type inference. Those important theorems I showed the detailed proof, so that this lecture is self-contained. Everything is written out in the slides, so you don't worry about consulting as a material or written lecture note. So this is about the contents of the lecture. The target language of type inference is the following set of untyped lambda terms given this BNF specification. Now we understand that this defines a freely generated set so that syntactic structure are understood completely. Therefore, the parentheses around this term and this term are omitted, right? Under our assumption that this BNF specification defines a freely generated set. However, in writing examples in string representation, there is no other way, unfortunately. So there is a way to represent structure by kind of tree-like syntax, but it's cumbersome. So usually we write examples still in string representation. In this representation, we use parentheses to disambiguate the structure, and we also use the following conventions. So E in the body of this lambda abstraction, this E is taken as large as possible. So that, for example, if we write down this sequence of symbols, this represent, so this E is taken to be as large as possible. So lambda x1 dot E, so E corresponds to rest of the entire term, so that this represent this kind of structure. Another convention is the following. Function application associates to the left. For example, this sequence of symbol represent this structure, so that this application associate from the left, so that this is the first application. So parentheses around this from the left to right, right? So this is the accepted convention in writing lambda terms, and these conventions are shared in functional language syntax. The meaning, semantics of lambda terms. This is not our main topic of this lecture. This lecture focuses on typing property, namely type inferences and their algorithms and their formal properties. However, intuitive meaning of lambda terms is useful in understanding typing property. So let's review meaning of lambda terms. So lambda x dot e. This term represents the function that computes the value e using a parameter x. The actual value of this parameter is given through application, this term. So this application term denotes the value obtained by applying function e1 to argument e2. This intuitive meaning is represented by the reduction relation. So this application of this lambda abstraction to some term, this entire term reduces to this term. This is the result of substituting occurrences of x in E1 with E2. The detailed understanding of denotational semantics or syntactic property of the reduction relation, these are not necessary to understand the rest of this lecture on type inference, typing system and type inference. And if you're interested in these, you should refer to some relevant chapter of my textbook or any other textbooks on formal semantics of programming languages. Actually, I have intention to provide a video lecture in some future dealing with these Lambda calculus, semantics, and syntactic property. So now let's turn to our main topic of type systems and type inference property. For this purpose, we define the set of types and review their intuitive meaning. So let B and T represent a given set, respectively base Ty of base types, and a countably infinite set T bar of type variables. Under this assumption, namely assuming that two sets, this set and this set, are given, and then the set type of types is defined by the B and F specification of this. By this we understand that this defines a freely generated set, so we omit parentheses around, and each element determines completely its structure. That is our assumption. And then let's review intuitive meaning of types, each components. So this are somehow obvious, but let's review this. T, so this component, is a variable representing some unknown type. And B, this represents a base type such as integer, int, or string. This is a type of function from T1 to T2. As I said, we understand that this defines a freely generated set. And so we omit this, that in this definition, parentheses. However, in writing example in string notation, we of course use parentheses to delimit, the structure and disambiguate. And also use the following notational convention, namely function type constructor, this arrow associates to the right, so that, for example, this sequence of symbols represent this structure. Right? So this is a definition of type, set of types. So next step is to define a type system. Before giving a formal type system, formal definition, let me try to give a motivation or intuitive understanding of a type system. So type system describes consistency conditions of an expression, including consistency of variable references and consistency of function applications to argument. Now, this consistency of function application are somehow obvious. However, the most important aspect of a type system is to specify this condition, consistency of variable references. So any language containing names, like a natural language or a programming language which contain variables. So fundamental consistency condition is the following. Any variable must be defined before its usage, right? This is the condition that must be satisfied in any language, including natural language. You can't say suddenly that some name, start by saying some name without a definition. That's meaningless. So to represent this first condition of consistency of variable references, a type system is defined as a system to derive a typing. This is a sentence of the form. This sentence is understood as under this environment, gamma, E expression has type tau. So this gamma is called a type environment or a typing environment or type assignment So in this lecture, I use a type environment, gamma. A type environment gamma is a function written in this way from a finite set of variables to types. The notion of typing that I just introduced is the most important building block in type theory, type system, and type inference algorithms. So let's try to understand this typing. For this purpose, let us consider an example, this very simple example of this one. F applied to x, f and x are both variables. For this expression to be consistent, there are two kinds of conditions. First one is that the variables f and x must be declared in the surrounding context, because this expression alone doesn't have any meaning, because we don't know what f is, what x is about. So mentioning f means that there must be some definition or declaration of f, same as x. So the surrounding context means some larger part, some part before this occurrence of this expression. In somewhere before this expression, there must be definitions of f and x. This is first condition. Second one is somewhat obvious. So this f is applied to this x, so there must be some consistency relation between function and argument, right? Function should be defined as a particular domain, and x must belong to that domain. That is a consistency condition, second consistency condition. So this second one is somehow obvious, and the important thing is about this one. So this consistency condition of variable references must be represented in a logical way in the type system. So these two conditions are represented by the typing of this form. So this typing represents the following fact. Under this environment, type environment, which describes the type of variables f and x. So this type environment represents the condition or property of the surrounding context where this expression occurs, right? So under this type environment, this expression has type tau2, right? So this is a typing, and this is a logical sentence called secant. This secant expressing the following two conditions I already said. The surrounding context contains a variable f of type tau1, L of tau2, and x of type tau1. And the application of f and x, f applied to x, evaluates to a value of type tau2. Right? So these conditions are represented in a formal system as a secant called typing. So this is the most important building block in type system. A type system is organized as a set of rules to derive typings. So those rules are called typing rules or type inference rules. There are two kinds of rules. First group correspond to constant, I mean the member of this C in inductive definition, inductive closure, definition of inductive closure. So for each member of this given set, we introduce an axiom. In the case of untyped lambda term, there are two kinds of members in this starting set of the definition of inductive closure. That is variables, and the other one is typed constant. I call this constant in the sense of the constant in the lambda term. I call the constant C in the sense of the definition of inductive closure, right? So it is obvious that the difference is obvious, right? So this and this are member of this C, and for each one, x and this constant CB, C of B, we introduce rule as an axiom. So we give a name of this rule, bar, and write down a template of typing, template of valid derivable typing. So this axiom indicates that set of all typings of this shape, set of all types that match with this template are derivable typing, same as constant axiom, right? So these group of rule axioms represent the fact that all the sequence of those forms are derivable. For constructed terms that are member of this set, that is, those terms constructed by some member of this constructor function, for each constructor function we introduce a derivation rule. In the case of untyped lambda terms, we have two constructors. One is lambda abstraction, the other one is application. So for each of these, we introduce the corresponding derivation rule, named abs for this lambda abstraction and app for this lambda application. So these are logical inference rules stating the following fact. So these rules state that if the upper sequence, those typings above the line, are derivable, then so is the lower secant. Right? This is a logical inference rule. So in the case of abs, this states the following fact. If this typing of E has type tau2 under the assumption that X has type tau1, then this lambda x.E has type tau1 arrow tau2 under the assumption that is obtained by eliminating this assumption x colon tau1. This is a little bit imprecise way of saying that I have noticed the definition of this one, and I will comment on this fact again later when I come to this abs notation in type inference system. By the way, so roughly this says what I have stated, right? So, and this is very natural way of understanding the rule for function abstraction. So function term has type tau1 arrow tau2 if the body has a result type under the assumption that this argument has the argument type. So this, you can understand that it's quite a natural way of expressing the necessary condition for the function to have a typing, right? The same as application. So in this case, we have two typings. One is this one, and the other one is this one. So this rule states that if both of this typing and this typing are derivable, then this conclusion typing, this lower secant, this typing is also derivable. So this is a typing rule, right? So, and its understanding. So in any logical deduction system, the basic notion is derivation. In the case of typing, in the case of type system, where we derive typing, the most fundamental or most basic notion is typing derivation. And explicitly understand this notion is important in understanding type inference system later we will be developing. So let's make this typing derivation explicit. So typing derivations are tree-like structure, concrete tree-like structure, starting with one-node derivations, which is obtained by applying axiom, instantiate axiom. So there are two axioms for untyped lambda term. One is bar and one is const. So this is an instance of bar axiom, right? So this is a trivial typing under x of type int. X has type int. It's obviously derivable typing, and this is a complete typing derivation. This is another example of application of bar axiom, where we have two assumptions in typing environment, f of type int or int and x of type int, and under this assumption, x has type int. This is another example of one-node derivation. In this case, is an instance of const axiom, right? So typing derivation in general are constructed by starting with these one-node derivation as a leaf and then extend leaf with inference rule. So this is a concrete example of complete typing derivation, right? So you start with this bar axiom and then apply this abs inference rule to get to two-node typing derivation of this typing. And also, this is one-node typing derivation, and this tree and this tree are combined by this rule APP and obtain this typing derivation. So typing derivation is a tree consisting of external nodes labeled with bar or const, and internal nodes labeled with abs or app, whose root node is the derived secant, conclusion secant, right? So this is an explicit definition of typing derivation. So the goal of this lecture is to understand the mathematically rigorous way a type system. So toward this goal, we define a set of typing derivations, right? So for this purpose, we introduce the notations. First one is this one, script D of this typing. This denotes a typing derivation tree with a conclusion secant, this one, conclusion as this typing. So this is a meta notation to denote the typing derivation tree. And then we define this notation, typing gamma tau. This is a set of all typing derivation tree under gamma yielding tau for some term e. Then we define the set of all typings, this set, to be the set of all these elements. This is itself a set, right? So this is a set of sets indexed by a pair, gamma and tau. Now, then we understand that a type inference rule generates an element set of this set of sets indexed by this gamma and tau from the other element sets. So this is a mechanical understanding of type inference rule. So in what follows, we make this understanding more precise. So namely, we interpret the typing rules as constructors of typing derivations. So we have 4 rules, 4 typing rules for the untyped lambda terms, right? 2 of them are axioms, bar rules and const rules, and the other 2 are inference rule, abs rule, and app rules. For axiom, bar rules, we interpret in the following way. Bar rules postulate the fact that this one-node derivation tree is in this set. Similar to const rule, this rule postulates the fact that this one-node derivation tree is in this set. So this is an interpretation of axiom, right? So axiom add member to the set, corresponding set. And for inference rule states the following. So in the case of abs rule, if you have a typing derivation tree with conclusion of this one in this set, then applying abs rule to generate a bigger derivation tree, this derivation tree generated by abs rule is in this set. So this abs rule acts as a constructor, taking an existing typing derivation tree and generate a new tree and add to this set, which is different from this set. Similarly for APP rule, this rule takes two derivations, D1 with conclusion this typing in this set, and this typing derivation tree with conclusion this typing in this set. And then you combine these two derivation tree and extend one node, this node, by application of this APP rule. You get a bigger typing derivation tree. And this tree is in this set. So APP rule acts as a constructor taking two trees and generate one bigger tree and add to this set. So this is the interpretation of typing rules as constructor of typing derivations. We are now in position to define implicitly typed lambda calculus as a formal system. So that set of untyped lambda terms with a set of typing rules form a formal system called the implicitly typed lambda calculus. So we denote this system small lambda. So terms in this formal system is not an untyped lambda term, but a derivable typing, right? So when a typing, so this is a secant, one sentence in this formal system has a typing derivation. This is a tree in this set. Then we write this way. So intuitive meaning of this notation is that this turnstile means something in the right hand side is provable from this system. So this lambda formal system proves this typing, right? So this typing is provable in this formal system. So typing inference infer a typing such that this typing is provable in this formal system. That is a precise and formal understanding of the implicitly typed lambda calculus. I now conclude this lecture with an advanced topic, that is typing derivations as inductive closure. As I said, this is an advanced topic that has not been explained in the textbook. So in the video number 3, I commented the following. Most of data structures in computer science, including expressions, types, and so on, and including proofs, are regarded as inductive closures. Now we understand that proofs are kind of derivation object, and in the case of type system, proofs correspond to typing derivations. Therefore, under this claim, under this view, typing derivation trees should be regarded as inductive closures, right? So is this exercise, which is a bit advanced. So define this exercise, asks you to define the set of typing derivations, this set, as inductive closures, right? So let me make some comment on this set by going back to a slide I showed before. So this slide is shown before that typing rules are interpreted as constructors of typing derivation. From this characterization, I hope you have noticed the similarity to the definition of inductive closure. So inductive closure, you start with the set of given constant C, and then generating by the constructor function f, right? So in this case, these axioms correspond to generating constant. So this 103 and this 103 corresponding to given constant in inductive closure. And then these inference rules are constructor taking an existing element, in this case existing derivation tree, and construct a new tree. Similarly for this rule, in this case, you take two existing trees and construct a new tree, right? So this corresponds to constructing a constructing function in the case of inductive closure, the set of f, right? Now go back to this exercise. Although you have noticed the similarity, but you should have also noticed that the apparent difference between the definition of inductive closures and this construction, right? So the definition of inductive closures, we construct one set that is a subset of a universal set. But in this case, we construct a family of sets indexed by this pair, right? So this exercise, in order to come up with a proper satisfactory solution to this exercise, you need to extend inductive closures as a set of this object indexed sets, right? And this is actually very common in computer science. For example, this extension is useful for mutually recursive language definitions. It is very common that BNF define a family of languages by mutual recursive specification. So I invite you to consider this exercise. So this is the end of this lecture.